get started right away with the first image, which is not coming up. Well, this is good. Technology moves forward here. All right, we have a countdown. T-minus 20 seconds. Just so everyone knows, I used to live in New York for many, many years. I now live down in Maryland. This is, so to me, it's like coming home to come visiting New York City, and it's very interesting. I haven't been to New York in about 5 years, and
closer to the mic.
Is it hard to hear me?
Yes, it is.
Oh, really? Okay, I will get closer to the mic. I've had people tell me I have a big mouth, so I'm very surprised that you're having trouble hearing me. All right, there we go. First image is up. This has everything to do with the Hubble. This is a picture of me in a cave in West Virginia called Castles during one of the cleaner trips of exploration. We were back in a section of the cave that not a lot of people actually like to go to. It's very muddy. It's very messy. This picture has everything to do with this picture. This is an image of a star that was taken around 1945. At the time, it was considered to be the best image of this star ever taken. This was a star that back in 1837 and then again in 1843 suddenly increased in brightness significantly, becoming the second brightest star in the sky. And then over fits and spurts over the next 100 years, it dimmed steadily. And it was first seen by John Herschel in the Southern Hemisphere. Didn't quite understand what happened with this star, and so there's been studies, and it seemed to have bright spots all around it. In the 1920s, they thought that it might be a cluster of stars. They really couldn't tell from photography on the ground. In 1945, an astronomer by the name of Enrique Gavriola in Chile took this set of exposures. They range from 64 seconds to 256 seconds, so you can see the increasing exposures. You work your way across. That's the highest exposure here. He dubbed this nebulous body here the homunculus, which is Latin for little man. He's almost like a little Pillsbury Doughboy. And this was considered the best image of this particular star. And I use this image in my book, Universe in a Mirror, and this particular star as a symbol of what the problem was with astronomy. And it's pretty evident to everyone in the world. Astronomers knew this very well, but, if you were interested in astronomy, you knew it as well, that, looking into space through our atmosphere was like I am right now. I'm totally blind. Is there an audience out there? I can't really see. I see fuzz. And that's really what the situation with astronomers. This is the image that they saw in 1945. And it seemed very obvious to everyone, let's build a telescope and get it up above the atmosphere. But it's not an easy thing to do, obviously. In 1945, you're before the space race has even become. It's more than a dozen years before Sputnik would be launched. But in 1946, this man, Lyman Spitzer, he at the time was an astronomer at Yale University, he was asked to write a paper for the first research paper of the Rand Corporation. They were forming after World War II, and their first research was going to be on the possibility of putting what they called a world-circling spaceship in orbit. Basically what we call today a satellite. And they asked Spitzer to write a paper on what scientific uses you could put to a world-circling spaceship. And he wrote an essay about the idea of doing astronomy from space. And he proposed in that year, and I'm going to move this up here so I can see it, he proposed in 1946 that we consider putting a 200 to 600 inch telescope in orbit. Now, I want to try to put some perspective on that. In 1946, the Hale telescope out at Palomar Mountain was not yet finished. That's a 200-inch telescope. It would be the largest in the world. It weighs 1 million pounds. They had been spending 3 decades building it, and it wasn't yet finished. It would be another year and a half before they get it done. And so, a year and a half before the Hale telescope is launched, is opened, Lyman Spitzer proposes putting a 200 to 600 inch telescope in orbit, 3 times bigger. It's very audacious. In his paper in 1946, he wrote that he hoped a telescope in space would uncover new phenomena not yet imagined and perhaps modify profoundly our basic concepts of space and time. Now, he spent the next decade, he was an astronomer. He soon became the head of the astrophysics department at Princeton University. As a young man, very successful astronomer. He did research. He was basically studied the gas that you find in nebulas in between the stars. But for the next decade, he also spent a lot of time trying to convince astronomers, the astronomical community, as well as the world, that putting a telescope above space is a good idea. Now, looking at that image I showed you just now, this one, it seems self-evident. But astronomy community was not convinced at all. They were worried about cost. They didn't think it would be effective or a practical idea. Spitzer would write papers. This was a paper he wrote in 1950 for the British Interplanetary Society on, this is a scientific paper on how you calculate the orbits of satellites. He'd write another paper. This is another one wrote for the Journal of American Rocket Society. And if you look at the very bottom here, interplanetary travel between satellite orbits, Lyman Spitzer. And this is one of the first papers to actually talk about the idea of transferring a spacecraft from one planetary orbit to another, which is basically standard operating procedures when we're sending craft to either Mars or Venus. And he's doing these papers because he's trying to explain the practicality and the technical possibility of doing space travel. He also attended a conference. This was a conference in Philadelphia at the Franklin Institute in 1956. He was one of the speakers. You can see, once again, how you can do astrophysical research with an artificial satellite, what you could do, and he's mostly talking about what you could do with astronomy if you got it into space. And he's trying to sell the idea of space. Astronomers, however, were still reluctant. He talks in one of his interviews later about how he'd give a talk at a scientific conference, and another astronomer came up to him and said, "Lyman, I admire your courage." And he was basically looking at him like Spitzer was a little crazy. Another astronomer by the name of Gerald Kuiper. You might have heard of the name Kuiper Belt. That's all the objects that are out beyond Pluto that are now Plutoids, possibly, not planets. Well, the Kuiper Belt was named after Gerald Kuiper. He's a very, very important astronomer from the 50s and 60s. Kuiper at the time said, "I would regard the funding of this project, i.e. a space telescope, hazardous and probably undesirable." So through the 50s, as self-evident as it might seem to you or I to build a telescope, Lyman Spitzer was not able to convince the astronomy community to do such a thing. And then this happened. Sputnik. In 1957, when Sputnik was launched, it changed the whole universe on the universe, no pun intended, the whole political landscape on the issue of space exploration. For the next 10, 15 years, we were in a space race with the Soviet Union, the United States, to see who could do the most successful missions in space. And money was rampant. They had lots of cash to do lots of things. They went to the moon, we know about that, and there was lots of money to do space exploration, and to do science, to do astronomy. Now, they did weather satellites very quickly, but the astronomical program was slow to get started. Part of the reason for that was, once again, the astronomers continued to be reluctant. And I should explain why they were reluctant. Now, NASA, I should say that almost immediately after Sputnik, NASA got on board and wanted to put telescopes in space. And they needed the astronomers' cooperation. They created an astronomy department, and they put this woman in charge. Her name was Nancy Roman. She was an astronomer, and she thought it would be a really cool thing to run the astronomy department at NASA and establish the space research for the first time for the next 50 years. So she went out, and she, with Lyman Spitzer, now was spending the early 60s trying to convince the astronomical community to get on board to build space telescopes. Now, a few astronomers came along. Spitzer made a proposal himself to build an ultraviolet telescope. Another astronomer by the name of Fred Whipple made a suggestion also to make a ultraviolet imaging telescope. A third astronomer by the name of Art Coe proposed to make a telescope to do spectroscopy in orbit. So there was some responses, but in general, the astronomical community was reluctant and hesitant. So this is now, even now after Sputnik. And the reasons they were hesitant were actually somewhat reasonable. And this, you have to understand the technical problems involved. This is the opening of space exploration. They've put weather satellites in orbit, which means they can take pictures of the Earth, get pictures of hurricanes, and then beam those images back down to Earth. So at first glance, you say, well, gee, why can't they do that in space for looking at galaxies and planets? But it's a wholly different problem. When you take a picture of the Earth looking down, the Earth is very bright. Hurricanes are very large. You don't need high resolution, and you don't have to have a very long exposure. So the satellite moving around the Earth at 17,500 miles an hour, which is extremely fast, can point down, take a snapshot, a millisecond amount of time, and have enough light to get an exposure. And because you don't need very good resolution, you can use television technology to beam scan lines down, and you see a hurricane. But when you're looking up at the stars, those objects are extremely faint. So you not only have to gather a lot of light, which means you have to do a long exposure, the equivalent of what you do for those photographers out there, a B setting on your shutter. You open the shutter and hold it open for days, if possibly, and close it. You need to, so that for one, you have to have total locked imagery. That telescope, moving 17,500 miles an hour around the Earth, has got to be able to point at those objects and hold those objects rigid for a very long period of time. And in the mid-60s, there was a great deal of questions. How the heck do we do such a thing? And they didn't really know. Then the second question is you've got to get the images down from space. Now, you can't use the television scan technology because it doesn't have the resolution you need. Film has great resolution, but when you put film up in space, you have a problem with radiation, cosmic rays. It slowly fogs after a period of time. And even if you get it up there and then even if you exchange film quickly so you don't have fogging problems, well, then the problem is how do you get the film back and forth? You can't send astronauts up on a weekly basis. You can't do recoverable crests. The military was doing reconnaissance with film, but they had lots of money, and they would actually have the craft come down and they'd snatch it out of the air by planes. But that was a lot of money, and the astronomy program that Nancy Roman here was running did not have that cash. And the astronomers who knew this, they understood that the cost to put one space telescope up in the 60s would have probably been $200 million in those dollars. Well, it cost about $20 million in those dollars to build the Hale telescope. So from their perspective, they could build 10 Hale telescopes for the cost of one space telescope that would be far less capable. So the astronomers in the 60s were very, very reluctant. So the result was this: nothing. In the 60s, you had a few small telescopes go up, but they didn't really produce much. They were ultraviolet, and they were doing spectroscopy. Their imaging was, actually, I've seen some of the imaging. It actually looks like, if those familiar with ASCII art on the web, or use ASCII text to make art, that's what a lot of those images were. They would put the X's and O's into a pattern, and that would give them their imagery. It was really not very good. But by the late 60s, things began to change technologically. The Gemini program had demonstrated you could do rendezvous in space. You could orient the spacecraft effectively. The military surveillance showed you could do high resolution in a lot of different ways. A lot of the video technology was advancing, and it gave hints that maybe that would be a solution to getting the images down. So by the late 60s, they became more conceivable, and the astronomers began to come on board. And so by, I'd say, 1972, NASA was beginning to move forward. And this man, Bob Odell, he got involved. As the astronomers began to get involved with the telescope and now begin to push it, he got involved in the early design work, the early concept work. They haven't a project yet, they're just talking about how they're going to design it. And in the early 70s, they're also beginning to see that the shuttle was going to be the next big thing at NASA. And so he and Lyman Spitzer began to think about how you could do a telescope and have it manned, have it periodically maintained by human beings. It seemed like a perfect mix of human and robot technology. And in 1972, Robert Odell became the project scientist for the Space Telescope project out of NASA in Huntsville. Now, you have to understand this, Robert Odell was an astronomer at Yerkes. He was head of the University of Chicago astronomy department, and he had gotten that job by the time he was 28. He was extremely respected, important astronomer doing significant research, some of it similar to Lyman Spitzer's about the gases in the nebula between the stars. And he actually gave that up to become manager project scientist, which is basically a management position at Huntsville for NASA. And he did that because the astronomers who were for this telescope, such as Lyman Spitzer and Bob Odell, recognized that to really finally convince the astronomical community to get on board, they needed to have an astronomer of some respect in Huntsville, where the telescope was going to be built, in charge, honchoing the project to make sure that NASA gave the scientists what they wanted. And Odell decided he was going to do it. They asked Lyman Spitzer if he would do it. Lyman Spitzer at the time was involved with maybe building a camera for the telescope and decided he was very comfortable in Princeton and didn't want to go down to Marshall, so he turned that job down and suggested Odell do it, and Odell did. So the two of these guys are now beginning to gear up the project to get the first design work going, developing it with the idea of having men service it periodically. Another scientist that came on board about this time is John Bacall, who unfortunately died about 2 years ago. John Bacall is most well known in the astronomy community. He calculated the nuclear processes in the sun. Back in the 50s, early 60s, they were trying to figure out how many neutrinos would the sun produce in its nuclear processes. And there was a scientist by the name of Ray Davis who built a telescope to detect neutrinos, and the place to put such a telescope is about 1.5 miles under the ground in the Homestake Gold Mine in South Dakota. And he wanted to know how many neutrinos would his telescope detect coming from the sun. And Bacall was the first one to work out the physics of that. He calculated how many neutrinos that Ray Davis would detect. Now, it turned out that actually Bacall's calculations were, I wouldn't say wrong, but they did not match the data. And in fact, it became a major physics problem because the amount of neutrinos that they were detecting were much less than Bacall predicted. And it turns out that was a major discovery in physics. It turned out they discovered, through Bacall's calculations, that neutrinos have a very small mass and they change states as they travel through space. And that came from his data. Because of that, John Bacall got a fellowship at the Advanced Institute of Science in Princeton, which is basically was holding one of the seats that Einstein once held at that institute. And Bacall, who had not been interested in astronomy or space astronomy much in his early history, heard about the Space Telescope in its early formation and said, that's a really great project. He decided to jot out a letter quickly, a short little letter, giving Bob Odell some encouragement and saying, look, if you ever have any questions or you need some help, just call on me. That's all the letter said. Bob Odell gets this letter, and he's beginning to form what he calls instrument science teams, which will start to work on the initial design work. And he'd been asking scientists for proposals to become part of those teams. He looks at the letter from Bacall, and he decides that's a full proposal. And he calls up Bacall and said, you've been accepted. Now, Bacall actually had doubts, not about the Space Telescope, but about taking on this job, because like Odell, if you start to do this kind of work, you're taking yourself away from scientific research, and you're doing more like management, reports, bureaucracy, paperwork, to try to convince funding to occur. There is some engineering involved. Obviously, you're trying to design the instruments and the basic concepts behind the telescope. Bacall had doubts whether he wanted to do that, but he decided, and this is the quote from him, the greatness of the project was too important to ignore, so he decided to go along. Now, this is now the 70s, and what you have in the 70s, and they've now begun to convince the astronomers. Let's give some time perspective on this now. It is self-evident that a telescope above the atmosphere is going to show us things that no one has ever seen before. Spitzer proposes it in 46. Sputnik happens in 57. This is now the mid-70s, 20 years later, and they still really have not put an optical telescope in space because of the technical problems and because of a lot of opposition. The opposition from astronomers has fallen away finally by the 70s. The technical problems have begun to disappear, at least the basic technical problems. They now see a way to do it. But you now have to convince Congress. And that's where Lyman Spitzer, John Bacall, and Bob Odell were crucial, because in the 70s there were repeated efforts to cut Hubble's, it wasn't called Hubble, it was called the Large Space Telescope at the time, to cut, not build it, not construct it. In the 70s, the American public and Congress was not interested at all in space exploration. They had decided that we have problems here on Earth that must be solved, and we don't want to spend any money in space. Now, there are maybe good arguments for that position. But in terms of getting Hubble funded, it provided a problem because the astronomers would go to Congress and say, we want to have a telescope above the atmosphere, and Congress was reluctant to give them the money. In 74, at the time it was only research dollars, preliminary development dollars, about $3 to $6 million a year, $6 million a year. In 1974, Congress decided to cut that $6 million entirely from the budget of NASA. No research on Hubble. A campaign with Odell, John Bacall, and Lyman Spitzer was able to get $3 million back so that research development could continue, but it stretched it out over a few more years. Finally, in 1977, NASA was going to list Hubble as what they call a new star, begin construction, full funding for the Hubble Space Telescope. The development project is going along. They knew what they had the designs. They were ready to build it. Congress saw that in the budget and blanched, and at first tried to cut it again. And once again, mostly John Bacall led a major campaign. Now, I want to mention that Bob Odell was working for NASA, so by law, he was not allowed to lobby. So he could only do things from behind the scenes. And he would basically provide a lot of information. As he told me, he could pick up the phone, and once someone called him, he could talk, there you're off. Or he would talk to Bacall about the typical things they were supposed to talk about and feed him as much information as possible. And Bacall would do the major lobbying because he didn't work for the government. And Spitzer as well would get involved in this, and they would come up to Washington repeatedly to see congressmen. Bacall told a story about how once he was going to see, at the time, Congressman Max Baucus of, I think, Minnesota or Wisconsin. Say again? Montana, thank you. That's right. Baucus at the time was a congressman, and Bacall goes into the office. The secretary puts him on a high stool and says, wait here. Baucus comes in, starts to fire questions at Bacall, one after the other. And Bacall said he had the feeling that if at one point he hesitated or seemed unsure of himself, Baucus would walk out. Now, he had no idea if Baucus was even on his side. Another congressman by the name of George Shipley at one point complained, we're exploding with telescopes. Why do you want another? They had just funded the VLA radio telescope the year before out in New Mexico, and they were wondering why you needed another one. And these guys fought for about 3 years, and they finally got the telescope funded. And that's a side note that's very interesting, and this picture kind of expresses it. The way they got it funded was this. It's called a buy-in. It's standard operating procedure in the D.C. area for any new project. And actually, it wasn't forced upon the astronomers or the engineers at NASA. It was forced upon them by the NASA administrator at the time, James Fletcher. Back in '72, they were holding a meeting in NASA headquarters with Fletcher, in which they were discussing just basic contractual issues, how they were going to pick a contractor to build the telescope. And they were trying to make a decision about the procedure in which to do that. And the meeting drones on for about an hour or two, and I've seen the minutes of the meeting. And during the minutes of the meeting, the engineers at the Goddard Space Flight Center mentioned that they think the telescope will cost about $500 million to build plus 1 year of operation. And later in the meeting, an engineer from the Marshall Space Flight Center says, no. That's a low-ball number. It's really going to cost more like $900 million, almost $1 billion, for construction and 1 year of operation. And then they finally make a decision on how they're going to actually proceed with figuring out how they're going to put out the bid for our contracts. Fletcher is sitting there kind of falling asleep during this meeting, it appears, until he hears those numbers. And he's aware of the politics. He's an administrator. He's not so much interested in the engineering, but he understands the politics of getting funding from Congress. And at the end of the meeting, he stops everybody and says, okay, we made a discussion about the contracting issue. That's wonderful, great. Whatever you decide is wonderful. But I heard those numbers of $500 million and $900 million, and that's impossible. I'm never going to get that through Congress. You guys build a telescope, pulls it out of the air, $300 million. That's it. Simplify it, but that's how much money you should do. And I can get $300 million from Congress. For the next decade and a half, that's what they had to make believe the telescope was going to cost. Now, it's interesting. What's interesting about it is that nobody involved in building the telescope simplified it. The astronomers didn't want to simplify it because they made it much simpler it wouldn't be able to serve them. They wouldn't give them the research data they needed. And the engineers didn't want to simplify it that much, because if they did, they wouldn't be learning new engineering. That was the whole point of doing this. They'd be doing something that had been done before, and that's not really why you do this. So together they just decide, well, we'll just go ahead and build it as it is, and when we run out of money, they'll come back and give us more, and that's what a buy-in is. And it's standard operating procedure in Washington. It's our way it always works. So for the next decade, Hubble is being built on a very tight budget. And this kind of dishonesty embodied NASA and the bureaucracy in that period of time especially. This is the period of time from about 1977 through the end of 1986, 87. And you'll know why I bring those years up in a minute. This, in the Marshall Space Flight Center, to give you another example of this kind of dishonest approach to build construction and design work. The Marshall Space Flight Center was run by a guy named Bill Lucas, and he would run what he called quarterly meetings in which everyone would come together and report on the status of the various projects that Marshall was building, one of which was the Space Telescope. But it was common knowledge everywhere in NASA that when you went to those quarterly meetings and you got up to give your view graph presentation, you were going to tell only good news. If you were to say anything about any of the problems you were having in engineering, you were called on the carpet. You don't do that here. These quarterly meetings were very, very carefully choreographed. And everyone understood that if you wanted to find out what was really happening, you went out in the hall and talked to people in the background. This was a picture that was taken, and it was given to me by, where's my, gotta have laser pointer. It was given to me by this man, Ed Weiler. Ed Weiler had taken over for Nancy Roman after she retired in around 79. He was basically the Hubble scientist at NASA and then became the chief of the astronomy department through the 80s and into the 90s. He's now head of science at NASA. He's come in and out for a variety of reasons. But this photo was given to me. They took this picture. This is Bob Odell, see no evil. This is Richard Harms, who was in charge of one of the spectrograph construction, hear no evil. Ed Weiler, speak no evil. Jim Westfall, who was doing the camera, do no evil. And to them, this epitomized how those quarterly meetings were being run and how NASA was being run in the 80s. It's funny, but the result of that was this. Challenger. They were not willing to face engineering problems honestly. They were not willing to face their budget problems honestly. And so they tended to look the other way when problems occurred. And the problem with the solid rocket boosters on the shuttle, you see that little light there? That is actually, you can see it here. This is a diagram, so you can see this is the solid rocket booster next to the big external tank. And that little bright spot there is the leakage coming out of the solid rocket booster because the O-ring was not working. And the result of that, in just a few seconds after this picture was taken, is that the external tank blows up and 7 astronauts die. The program was halted. In terms of Hubble, that accident delayed the launch of Hubble for another 3 years. So it wouldn't be launched until 1990. It also was demonstrated very clearly that NASA's engineers had been aware of this O-ring problem for several years and been trying to get managers to pay attention to it. But to deal with the problem would, of course, involve cost and facing reality. And at the time, that was not the culture of NASA. It was more like this. Oh, went back too far. More like this. I mean, the engineers and the scientists knew this was wrong, but they had to work within the framework that they were stuck in. Hubble was meanwhile being built on a crippled budget. There was constant pressure to get things done right. Finally, in 1983, they kind of get things organized. I'll just take that off because they get things organized. They realize they need more money, and suddenly there's a big influx of money. This is how a buy-in works. The project's already has been funded for years. You've spent a lot of money. You now go back to Congress and say, "Look, guys, we need more money to finish it." And at that point, Congress says, "Okay, we got to give it to you. We want to get it done." So they give them lots of money in '83, and they got the telescope finished. By '86, when the Challenger accident happened, they were only like 8 months from launch. They were just about ready to launch. Finally, in 1990, they launched. There was great pressure to get that first image. Once again, people had been waiting decades for that first image above the atmosphere. Everyone, once again, scientists knew this. But I think, General, everyone's here today. This is something that they found out when they were building the telescope. Astronomers would come across stories repeatedly about ordinary people who were intimately aware of the possibilities of getting a telescope above the atmosphere and that it would see things no one had ever seen before. So the anticipation of that first light image from Hubble was gigantic. Unfortunately, that was the first light image. Now, some of you might remember this. Most of you, I think, will. Some people might know of it vaguely. When Hubble was launched in 1990, the first images came back, and for some reason, they didn't understand why, the light was spread over a large area. It did not give a sharp, focused image. Now, within the bowels of the Space Telescope Science Institute, which manages Hubble, and the Goddard Space Flight Center, which was operating Hubble engineering-wise for the scientists at the Space Telescope Institute, there was great consternation. They didn't know why they couldn't get the telescope focused. I talk about this part of the subject at much greater length in the University of Mira. But what is wrong? They couldn't get the telescope focused. They kept moving the primary mirror. It wouldn't be in focus. Finally, one scientist by the name of Sandy Faber realized that it was something called spherical aberration. Now, spherical aberration, what that means is that the primary mirror of the telescope had been ground much flatter than it was supposed to be. And that produces a situation. Another way to describe it is this. Imagine you have the letter C. That's the shape of the mirror. And you draw a straight line out from the letter C. If the mirror is curved properly, all the light will focus on a single point along that line. With spherical aberration, light at different positions on the C will focus at different points along that line. And that's what was happening. And they didn't know why. But what it did mean is that the first telescope that was going to look at space above the atmosphere sharply was out of focus. There were people in the astronomy community that thought, my God, this is going to kill astronomy for decades. Careers, they thought their careers were destroyed. They were horrified. It was just Jim Westfall, the man who was in charge of building the camera during this period of time, hated big science projects. He didn't originally want to do it. He liked to work on small projects where he could actually get in there and solder the circuit boards himself. He liked to tinker with things. But he was convinced to become the project scientist in charge of building the camera because, once again, the project, this is too big. It was going to be big. And he had scheduled... He had guaranteed time for the first year to do research because he had sacrificed so many years building Hubble. He had scheduled to look at every possible interesting object you could imagine to take pictures of it because who knows what he was going to see. And when this was discovered, he was crushed. They asked him at a conference to give a report on what he thought the results were. He didn't even get up from his seat. He sat in his seat and only spoke for about a minute. He basically said, my whole program's destroyed. And he had wasted 14 years of his life. He was now 62, and it's lost. Oh, that's an interesting graphic. All right, we're going to have to find... we have technical problems here, and I'm going to have to fix them. I will go there manually. You don't want to see that again. Okay, there. What they figured out, Sandy Faber actually did this with spherical aberration. The bottom image is actual Hubble images at different exposures during that period of time. It produces these rings. In specific, they called this the smoke ring image because it had a very sharp, defined edge. And what they did is they took software and they tried to simulate different prescriptions for the mirrors, different shapes for the mirrors to see if they could duplicate these images. And what they eventually found was a spherical aberration, and this is a simulation here, and it matches perfectly. This is the actual view graphs that they showed to the scientists in June of 1990 to show them what was wrong with Hubble. And Westfall's response is the one I described to you. NASA immediately put together a commission to try to figure out what went wrong. I now have to go back in time to when they were grinding the mirror. During that period of time when they had this make-believe budget of $300 million. The company that had been hired to build the mirror for NASA was a company at the time called Perkin-Elmer. They made optical equipment for the military and for astronomers worldwide, very high-level equipment. They had ground mirrors for the military, for reconnaissance for years. They were very highly respected. But they were working under a very tight budget with very little time and very little staffing. And what happened when they started to grind the mirror, they were 6 months behind schedule. And in order to understand what the shape of the mirror was going to be, they had a piece of equipment called the null, a reflective null corrector. And what that null corrector was is it's made up of 2 mirrors and a lens. And it was placed in the ceiling. Let's imagine for a minute this is Perkin-Elmer's factory right here. The mirror itself was on tracks. They'd roll it out into the room where they do grinding. They'd roll it back into this room, let's say, set it up directly under the null corrector, which was set up in a room overhead, so that this field lens was sticking out below the floor of the room overhead, above our heads about 30 feet. In a very inaccessible place, actually. Now, the technicians that had to put this null corrector together had to place the 2 mirrors at a very specific distance from each other, and then place this field lens at a very precise distance from this point, which is the center of the curvature of the lower mirror. In other words, light would focus at this point from the lower mirror. It's a point in space. They have to get this lens the exact distance to that point in space. And the way they did it, the bottom mirror, the field lens, was set on a set screw so it could be moved up and down. And they created what they called a measuring rod, which was made out of invar material. Invar material is material that doesn't stretch or expand or decrease with temperature changes. So it has a very firm shape. And they fitted this measuring rod, you can see it here in this diagram, into position, and they placed it so that this distant point was here. And how did they know where to place the end of the rod here? What they did is they put a cap on the end of the rod with a hole in the center. Now, and they were going to aim a laser then at the center of the rod. And it's very important they hit the center of the rod because, the rod is rounded at the top. So they want to make sure they're hitting the center of it so they'll get the exact right distance. So they put a cap. They painted the cap with non-reflective paint. So if the laser hit it, it wouldn't bounce back. You wouldn't get a reading. You put it over the hole, and that's when you get a reading. So they did this. They put it in position. They got it fit. And then they proceeded to try to lower the field lens at the bottom to match the distance as told to them by the measuring rod. And they turn the screws, turn the screws, turn the screws. They can't turn anymore, and it's not going down far enough. And the technicians, at times late, were 6 weeks late. We should have been starting grinding the mirror 6 weeks ago. We don't have a lot of money. We got to figure out how to get this done. So they said, all right, well, look, we'll take 3 washers. We'll take the field lens off. It's 3 screws. We'll take 3 washers. We'll flatten them down a little bit to give us enough distance. Put them back, put the field lens back in place, and that'll give us enough flexibility to turn the set screw down a little more to get it in the right position. And that's what they did. So this reflective null corrector was set at that position when they were grinding the mirror. The problem is it was the wrong position. Because the reason that the field lens at the bottom had to go lower than the set screws was because the laser that was pointing through the hole, supposedly, of the top of the measuring rod as designed there, this is the laser going through the hole in the center, hitting the top of the measuring rod, it didn't actually do that. It hit the cap, and there had been a small chip on the non-reflective paint. And it actually gave them a distance off the top of the cap, which was 1.3 millimeters above the top of the cap. That, therefore, had them lowering the field lens 1.3 millimeters lower than they should have. Now, the null corrector was new technology. It was one of the reasons Perkin-Elkins got the contract, because it was a much easier, simpler way to measure extremely precisely the shape of the mirror. In fact, they had so much faith in this technology that Perkin-Elmer just didn't do any other secondary tests to back themselves up. Now, one of the reasons they did this, once again, they were under tight budgets. They had no time. NASA, similarly. At one point, the optical engineers at Perkin-Elmer actually made a report suggesting that they do a second coarse test, very simple test, just to check for some gross errors in the reflective null corrector. And they decided not to do it because they just didn't have the time or money. Interestingly enough, they did do tests later on, I talk about this in the book, where they actually aimed the mirror, they were trying to just get gross measurements of the mirror for other purposes, and this was using a different kind of null corrector that was much coarser, and it showed that the mirror was not in the right shape. But they had so much faith in the reflective null corrector that this was not a case now of budget, this was a case of human error. The engineers involved just dismissed it. They said, no, the equipment we've got is far better, it's got to be right. And so in a certain sense, the budget problems caused the problems, but in another sense, this is almost like a Shakespearean tragedy, human flaw. It was just human beings not being perfect and missing something that was staring them in the face. Now, this man, Ed Weiler, who was, as I said, head of the astronomy department at NASA, when he came into the program, he realized that they had not actually done any serious thought about how Hubble would be maintained. And in 1983, 7 years before the telescope was launched, he sat down and wrote a white paper saying that, look, guys, there's been talk of taking Hubble, bringing it back to Earth to do maintenance. There's been talk we'll do weekly missions. There's been talk how we will schedule shuttle missions on the fly when we need it. And this is all kind of like off the cuff, and it's not smart. I want us to set up a precise, specific schedule, know what missions we're going to do, know when we're going to do them, and know what instruments, update instruments, repairs, what we're going to do in each of those missions. So under his leadership, back in the 80s, they decided to build a second clone of the original camera of Hubble, just in case something went wrong. So they built a second clone. In addition, they started to build an infrared instrument that would be brought up to Hubble in later years, like 96. That was the plan. And they also built some additional backup equipment, additional gyros. And his plan was that when Hubble would be launched, when it was launched, 3 years later, there would be a servicing mission to bring a new camera up, a new spectrograph, and additional equipment if needed. So when Hubble was launched in 1990 with this problem, they were already prepared to repair it. What they decided to do with the clone camera was they would just simply, you have to understand now, the mirror had been ground incorrectly, but it had been ground incorrectly perfectly. It was just to the wrong prescription. Well, if you know what that incorrect prescription is, on the new instruments, you can just put a compensating prescription to correct for it, like putting on glasses, and those instruments will be perfectly sharp. This was trivial correction on new instruments. So the clone camera was very quickly able to be corrected and to be fixable. They also improvised an additional instrument to be launched in 93 called CoStar, which would actually make it possible to correct the remaining 3 instruments that were up there by inserting additional mirrors in the light path of each instrument that would put in the corrective prescription, basically putting glasses in front of each instrument. That was quite complicated because what CoStar was basically like 8 arms would swing out and insert mirrors in the light path for each of those 3 instruments in multiple different light paths, and they have to have 2 mirrors for each instrument, and it has to be precisely placed to bring the light back down. It basically brings the light up, down, and back into the instrument very precisely, and you can't block. Very complicated instrument. And they built these things, and in 1993, they did what is probably the most famous, I think, one of the most famous and most watched shuttle missions of all time, which was the December 93 repair mission to fix the Hubble Space Telescope. They did 5 spacewalks over a period of 5 days. That was the most ever done on a shuttle mission. They now do this pretty routinely, but that was hard at the time. And they replaced gyros. They put CoStar in. They took the original camera out. They put the new camera in. They installed CoStar, and they made some of the repairs. They put blankets up. They noticed some damage to the insulated blankets. They replaced the solar panels. I haven't even talked about the solar panel problems. The original solar panels were not designed properly, and they would shake the telescope. So imagine if you're trying to take a picture on a long exposure, and periodically the wind blows and you shake. And it takes about 10 minutes to settle down. And then the sun comes up and you can't see anything. Every orbit, they only have 45 minutes of darkness, and if it would take a half hour for the telescope to settle down, they had a problem. And that was the solar panels shaking from thermal changes from darkness and light. So they had to replace the solar panels. They did this mission, and then they waited. Would it work? This is a picture, what the astronomers call second light. First light is, of course, the first time you take the lens cap off of a telescope and you get to see the light passes through it completely and you get to see things for the first time. And, of course, we know what that looked like on Hubble. It wasn't good. This is what they call second light. And this was actually a very private ceremony. They didn't have a lot of cameras. They kept it quiet. This was in the Space Telescope Science Institute. You can see Ed Weiler there. He said this was the worst 3 seconds of his life. They're all looking at the computer screen to see the first graphic image come up. And this is a grab off of a DVD, and they actually videotaped this. And what happens in about 1 second from this image is you suddenly hear cheers. This man here, Jack Traeger, who was a chief scientist for the new camera, he screams out, 1 pixel, because all the light was concentrated in 1 pixel, basically, right here. You can see the old image versus the new. This meant that Hubble was going to be sharp. It was going to give them a precise image. They were going to be able to do the science they wanted. It means we would be able to see the universe as it actually is for the first time. This is one of the very first images that came out of Hubble right away. This is the supernova from 1987. It's the only supernova since the era of the telescope that's been seeable by the human eye. It occurred in 1987 in the small Magellanic Cloud. Previous images by Hubble and ground-based telescopes were not very clear. This image shows this is the actual debris from the explosion. That's not a star. That's the debris from the supernova explosion expanding. This is an old nebula, planetary nebula that surrounded the star that had been formed like 20,000 years earlier that has now been lit up by the light from the supernova explosion. You see this bright spot here? That's a brighter spot because the debris from the explosion and the energy from the explosion was very fast, but it had to travel a long distance, was steadily over time, many years, beginning to hit the outer ring. And Hubble has been following this now for almost 20 years now. You can see, if you look at these images very closely, you see that bright spot on the rim. Notice there's a new bright spot forming up here. See new bright spots forming here with time. More. See, they're all brightening. What's happening is the debris in the center. See how the debris in the center is also expanded and changed? I mean, this is the only telescope in the universe that can show us this stuff is Hubble. We're actually watching the debris of a destroyed star expand as it spreads out. And what's happening here is this pearl of necklace brightness is produced by the debris as it flings itself outward against the object. And over the next few decades, this star is going to continue to, this form of supernova remnant is going to continue to change drastically. Eventually, this material is going to hit the outer ring as well. It's going to take many decades, but when it does, we're going to see some light show, and we'll need an optical telescope in space to see it. And I'm just going to give you a few images here. I'm not done by this story. I'm not even half done, but just to give you, now that Hubble's fixed, we start to see, once again, it's just remarkable. This is Hubble periodically takes pictures of Mars. We can track its weather formations. You can see storm clouds, dust storm clouds above the north cap, clouds down here. This is dew in the morning. It's Martian dew, which is pretty faint, but it's still dew in the morning on Mars. Jupiter, when comet Shoemaker-Levy crashed into Jupiter, it was Hubble that was able to get the real pictures of the impacts on the planet. Imagine a comet hits a planet. And the scientists have said, well, we know that happens, but the odds of that happening when we're around observing it are really slim. It's going to, they happen maybe every 10,000 years, and human history isn't even that long. Well, we were lucky. It happened in the last 2 decades, and they got pictures. Hubble showed the ripples running outward from within the atmosphere of Jupiter. Spectacular, bigger than the Earth. Of course, we've been tracking the great red spot in the storms of Jupiter using Hubble. When they had Galileo orbiting Jupiter, and it was able to take a lot of great pictures. But Hubble, from Earth orbit, can do much of the same thing when they give it some time to look at Jupiter. And this is the great red spot. This is what they call red spot junior, which only formed in the last 10, 15 years since Hubble's been looking. And only in the last year, red spot 3, and I don't know if they have a name for it, has formed. They think these two are going to finally merge. They might merge with this spot as well. They're storms. They're storms that are bigger than the Earth on Jupiter, and Hubble is giving us really beautiful pictures of it. This is not from Cassini in orbit around Saturn. This is from Earth orbit taken by Hubble. Eagle Nebula. Now, to us, this is beautiful. It's like someone said to me in the reception, this is like artwork of our time. And it is, because the universe is a beautiful place. But it's also science. What they're learning is that the stars out here that are very bright, these are very hot stars, supermassive stars. And what they do is their light hits the dust cloud, and the light itself photoevaporates the dust and destroys it over time. And that's why you get these wonderful carved shapes as it slowly dissolves it away. It's kind of like if you were to pour water on ice. You know how ice will melt in that strange forms? That's kind of what's happening here, except it's on vast scales. One of my personal favorites. I mean, it's a supernova remnant, but you know, I'd almost think this should be a picture from Wuthering Heights. It's just beautiful. It's the universe. Planetary nebulars. We get to see them for the first time and begin to understand their shape and how the stars are evolving with time. And in fact, some of these shapes are inexplicable still to the astronomers, but they're beginning to understand. They can take the data here, which is sharp, and begin to form reasonable theories about what's happening. They're not guessing from a fuzzy image. They actually have data that can give them, they can build models to understand what's going on. They think with a lot of planetary nebulas, you've got binary systems, and the two stars themselves are circling around and shaping the gas in these weird patterns, kaleidoscope-type patterns. Red rectangle. This is another one. It's just Ant Nebula. Galaxies. This is one galaxy in front of another. They don't think these two galaxies have anything to do with each other. It just happens to be one is in front of another. It's just billions and billions of stars. Very likely with many planets around them. This is one of the more famous amateur astronomy galaxies. You can look at this with a pretty much easy amateur equipment, but look at Hubble. And it's hard to understand the resolution of Hubble. You can actually zoom in into these areas and you wouldn't see pixels. When you get the highest resolution image on the Hubble website, you're not getting the highest resolution image. A highest resolution image would fill this wall, and even then, it's gigantic. These images take your breath away. This is a galaxy. It's many hundreds of millions of light years away, and yet here in that galaxy, there is a nebula, a star-forming region so large that you can see it. And they've taken a picture getting up close. And they learned something about star formation from that. One of the images I should have put in here, and I'm sorry I didn't, and I only realized this afternoon when I couldn't do it, was I should have put the ultra-deep field image. One of Hubble's greatest contributors was cosmology, where they took the telescope and they aimed it at a blank spot in the sky, about the size of a grain of sand looked at from 6 feet away. And they kept the telescope open. They did several of these. They did a north deep field, and did a south deep field, and then they did an ultra deep field. And the north deep field was about 10 days long exposure. Same with the south. The ultra deep field was longer. It was the equivalent of 400 orbits. It was a much longer exposure, much more carefully done, with a much better camera. Well, the ultra deep field, I'll use that as the best example. This is a blank spot in the sky. They purposely picked it because there are no stars known to be there. It's looking up out of the galaxy, so you know you're not going to get much there. In that image, they see 10,000 galaxies. That telescope is looking at the very edges of visible light. It literally is looking as far as the eye can see. Because as you start to look far back in time, light gets redshifted. Because the universe is expanding, the farther away you go, the more light gets shifted into the red end of the spectrum. You go farther, deep enough and far enough away, all light will get shifted into the infrared where the eye cannot see it. And so, when Hubble took the ultra-deep field image, it took an image that was looking as far as the human eye could see, because beyond that point, everything is in the infrared, and you cannot see it with the human eye. It's one of the reasons the James Webb Telescope that is going up next decade, it's not an optical telescope, it's an infrared telescope, so astronomers can do research at the very farthest edges of cosmology. I didn't show that. I'm sorry I didn't bring that image, but it's one of the key discoveries of Hubble. Hubble was key to the discovering of the acceleration of the universe. It contributed to that discovery. It's one of Hubble's great contributions. And all these images have reshaped our concept of the universe. And one thing they have to always remember, and astronomers sometimes forget it because they get so caught up in the data and the information and trying to figure out what's going on, is that the images are spectacularly breathtaking. And why are they breathtaking? Because they are an expression of the beauty of the universe right before our eyes. Hubble contributed other ways as well. During the period after Hubble was launched, they did additional servicing missions. It's important to talk about that because it's also it's influencing human history in ways that I think people aren't yet conscious of. Those servicing missions, there were 3 more, one in 97, let me get this up, one in 99, one in 02. During those missions, they replaced the gyros of Hubble. Gyros have a tendency to fail after 5 years. They're moving parts. They get worn out. There's no way around it. They have not been able to solve this problem. So they've replaced the gyros on Hubble at least twice, all 6 gyros. They brought up a new spectrograph called STIS to replace the one that was up there, state of the art. They added a new camera called the Advanced Camera for Surveys. That was the camera that took the ultra-deep field, very sophisticated camera. They added NICMOS, which is an infrared camera, taking infrared light. Then they repaired NICMOS when an infrared camera has to work in extreme cold because heat is what it's really measuring, and you don't want to get heat from around you just want to get heat from what you're looking at. And so it has kind of like a Dewar. It's in a refrigerator. Well, the coolant in the original refrigerator leaked. So they came up with a design that was a permanent Dewar that wouldn't leak, and they came up and they put it up and they fixed NICMOS, and it works today. They put up new solar panels. In fact, the Hubble that is in orbit right now carries no instruments from its original launch. It's all state-of-art. Those 3 servicing missions are influential in a sense that they demonstrated the importance in space exploration of a teamwork effort between robots and humans. While robots are cheaper and faster to build and can do many great things, they don't have a great deal of flexibility, and if something goes wrong, they can't do anything about it. If Hubble had been a robot telescope that humans couldn't fix, it would have been useless after its launch. It never would have been fixed. Humans are expensive to put in orbit. It's difficult to do it, but it's worthwhile doing it once in a while because they can fix things, and it's a demonstration of that. On top of that, the reason we go, and Hubble demonstrates it, one of the reasons I think people are passionate about Hubble is because not only can they see these spectacular images of the universe, excuse me? Oh, okay, I'll just try to keep talking into this. Not only the image is beautiful, but we feel a connection with Hubble because we see human beings fixing it periodically, updating it, making it better. In fact, there were plans, after those 3 missions, to do a 4th servicing mission. This was back in 02. They needed to do a servicing mission to go back to Hubble because, once again, the batteries that were in Hubble has batteries. At every orbit, the solar panels absorb energy. They hold that energy. They get recharged for the dark period of the orbit. Then they get recharged again. In fact, these batteries were designed around 1978, were installed in the telescope in the early 80s. And they've been recharged probably 100,000 times. One technician in a control room at the Space Telescope Institute once told me, they are the best rechargeable batteries that have ever been built. But as you can see from this graph the engineers put together back in 04, over time rechargeable batteries start to lose rechargeability and they start to decline. In 04 they anticipated that sometime around 08 they would not be able to get enough sufficient power from those batteries to keep the telescope operating. So Hubble needed a new set of batteries. That's what the service mission was going to be about. Similarly, gyros fail every 5 years. There are 6 gyros on Hubble. The ones that are up there were all brought up in around 1999. In fact, I think 2 or more were replaced in 2002. Well, right now, 2 of those have completely failed. A third is unreliable. And the 3 that are left, they are very careful how they use them. They actually try to keep the telescope now on either 1 or 2 gyro modes, which kind of limits the quality of the images. So they needed to bring more gyros up. In addition, they had built a new spectrograph called the Cosmic Origin Spectrograph for $65 million. It's sitting at Goddard, ready to go. They built a new camera. They were going to take out the 93 camera that fixed Hubble. Over time, CCDs, that's what the camera uses to take pictures, just like your digital camera, those begin to decline in space. And so they needed a new camera, state-of-the-art. So they were going to put this camera in place of it. This cost $83 million, ready to go. And of course, too, it seems like it's obvious you should keep Hubble going. We don't have any other optical telescope in the works. You need to have something. It's a part of this, the toolkit that astronomers use to study space, and it's part of what we want to see the universe. And then this happened. And this is, once again, a similar story to the Challenger accident. This is the Columbia, bits of Columbia coming back to Earth. And this was it's a shockingly similar story to what happened with Challenger. There had been evidence that foam was coming off the external tank from day one of the shuttle program, and nobody could see it. Now, that's kind of similar to what happened to the mirror on Hubble. This is human error, just human flaws, and people are not perfect. But when engineers did raise the issues, management at NASA wasn't willing to face the problem and ignored it. And this was a very serious problem. Because of the Columbia accident, NASA got completely restructured. The administrator of NASA at the time, faced with great pressure and a completely restructured program, made a decision to cancel that last servicing mission. This was in 2004. That administrator here is Sean O'Keefe. He was administrator of NASA for, I'd say, the first half of the Bush administration. He made this decision, I think, for some reasonable reasons. There was some logic to his thinking, though I don't agree with it. In fact, almost nobody did. First of all, his decision was made in the context of Bush's vision for space exploration, which I must tell you is probably the most thought-out, detailed goals for NASA that NASA has received since Kennedy. Very detailed, very thoughtful, long-term plan for what NASA should be doing, giving the agency goals. The Columbia Accident Investigation Board said very clearly one of the reasons NASA had a problem was that the Congress, the President, and the American people had not given NASA a goal, a plan, a structured principle for what it was working towards. And this plan at least gives NASA that, and it's focused on exploration. Well, from Sean O'Keefe's point of view, the Hubble mission, it was going to be very expensive to do this, and he wasn't going to be given much money. So he thought, well, if I could get rid of that Hubble mission, I might be able to save some cash. And for Sean O'Keefe, there were safety considerations. The Columbia accident, this telescope got damaged on launch. Well, if you take a shuttle and you are taking it to the International Space Station and it gets damaged in launch, you have time. The people can wait it out until a rescue mission can be put together and launched to bring people back. There is safety there. They call it a safe haven. If you go to Hubble, you cannot go to the International Space Station. The orbits are configured in such a way that you can't go back and forth between the two. If you choose to go to Hubble, that's the only place you can go. And a shuttle, if it was to be launched and damaged, and therefore could not come back to Earth, you'd have to mount a rescue mission fast, because the shuttle only carries supplies for its crew at most 30 days. So from O'Keefe's position, this shuttle mission to Hubble, which was the only one not going to ISS, had danger involved with it. In addition, and this is a point that the astronomers like to not me talk about, but I'm going to talk about it, during the 90s and the early part of this decade, the aughts, the astronomers themselves were issuing reports suggesting that Hubble itself be lowered in priority in its terms of its maintenance and use. They had a lot of logical reasons themselves for doing this. They wanted to get an infrared telescope in orbit. That was James Webb. Hubble was already in orbit. They'd rather focus on getting a new infrared telescope than flying an optical telescope. A new optical telescope would have to be much bigger than Hubble to really give them big benefits, and to build a really big orbiting telescope that's optical is extremely technically difficult. So they made a strategic decision to say, well, after this last servicing mission, Hubble will go into a no-maintenance mode, we'll use it, but we'll keep it on a lower priority. Well, Sean O'Keefe sees these reports from the astronomers, and let me just quote from this particular report, just to give you an idea of where they stood. The astronomers said they recommended a much more economical style of operation after 2005, with no servicing or instrument replacements after 2005, a final boost into a higher long-lived orbit, and possibly reduced instrument complement and limited modes of operation. So Sean O'Keefe he sees this from the astronomers themselves, and he says to himself, well, I'm not going to be able to launch the servicing mission before 05 anyway. And since they seem to think that we could do without it, why don't I just cancel it? I like to say this, there's an old saying, be careful what you wish for, you might get it. And in this case, the astronomers got it. They canceled the mission. Now, the response of O'Keefe's decision to cancel the mission was pretty unanimous. Hundreds of editorials. NASA started to get 400 emails a day, letters and emails a day saying this is a dumb decision. There was a website put together with a petition. They gathered within weeks 40,000 signatures saying we should not cancel the servicing mission. O'Keefe was forced by Congress to put together a National Academies panel. That panel, its job was to assess his decision, and he was starting to advocate, let's send robots to Hubble to repair it. And so that panel's assignment was to try to figure out whether or not a robot mission made sense, or we should go back to the shuttle mission, or we should not do anything at all. Their decision, in the end, was to basically say that O'Keefe was wrong, that in fact his decision was incorrect. They were very polite about it. They basically said, well, I won't use what they said he was wrong. And in fact, within 5 days of the release of that National Academies panel, Sean O'Keefe resigned. He couldn't stomach the idea of sending people to Hubble. And I personally think, and this is on my part, my own opinion, it's not based on fact, it's only based on my personal experience of seeing the man O'Keefe and during testimony, as well as once in a while press conferences talking with him. The Columbia accident was a great trauma for him. He was a bean counter. He was a bureaucrat. He got the job as head of NASA as like a bureaucratic promotion. He was an appointee. He had not been prepared to deal with death. And when that Columbia accident happened, he had been on the runway with the families of the astronauts to congratulate them on the return of the mission. And instead, his job was to tell them that their husbands and wives had died. And it was a great trauma for him. And I don't think he had the mental ability after this fact to send humans back up into space at all. And he was going to resign anyway. But when he was told he had to send a mission to Hubble, he couldn't do it. And he resigned. And the man that replaced him was this man, Michael Griffin, who was actually an engineer. He actually, in his early career, worked on Hubble as an engineer. He's been an astrophysicist. He's got like 7 degrees in aviation and aerospace. He's a space cadet. He's, in fact, the first NASA administrator in history who is an actual space cadet, knows something of the aerospace industry, which puts him he's very interesting. He's the first administrator I've dealt with in years who, when you ask him a question, he'll give you a blunt, honest answer every single time. If he doesn't know the answer to something, he will say, I don't know the answer to that, but I'll find out. It's brought an amazingly refreshing atmosphere to how NASA is treated by Congress, because congressmen now know that he's not really going to do a buy-in for them. He's been telling them, you're not giving me enough money to do what you want me to do, so I'm not going to do it as fast as you want me to do it. It's a straight answer, and he's building the program into the future with the actual reality of what it's going to cost and how it's going to unfold now, rather than wait until there's disaster strikes and there's a problem. And what that's forcing Congress to do is face the reality. For one thing, Bush's vision has what I consider a significant flaw. It retires the shuttle in 2010, but it doesn't have a replacement man's capability for the United States to fly until 2014 or 15, which means we go through a 5-year gap where we, as a nation, cannot put people in space. We can't bring our own astronauts to our own space station. And Griffin has told Congress this gap is going to actually get longer because I don't have enough money to get Orion up as fast as you want. And Congress wants them to get it up like sooner, so there won't be a gap. And what that's doing, it's an honest approach which is actually forcing Congress to give NASA more money right off the bat today. It's a very different situation. Well, Mike Griffin, he immediately, in his initial testimony before Congress when they were nominating him for the position, said, I'm going to revisit that shuttle mission to Hubble. And he reinstated that shuttle mission. It's now going to go off in October, on October 8th. They're going to put in COS, the spectrograph. They're going to put in the wide field camera. They're going to give it new gyros and batteries. But they're going to do more. In the last 5 years, Hubble's advanced camera for surveys, that's the camera that took the ultra-deep field, it has failed. It has a circuit board that doesn't work. So they don't have that camera right now. In fact, Hubble's only camera that works right now is the 1993 camera, which produces good science data, but you don't see beautiful pictures from it very often anymore. And the other instrument that's failed is STIS, which is a spectrograph. Hubble doesn't have a spectrograph right now. On this mission, they're going to try to repair both of them. And it's really audacious because STIS, to take the circuit board out and replace it, they have to unscrew 111 screws. And to take ACS out, the advanced camera, they got to remove 32 screws. And they've actually worked out a system where they think they can do it. It's going to be an incredible mission in October. Stand by. They're also going to do another thing. They're going to add a docking port to Hubble so that down the road, a robot or even a manned mission, like the Orion spacecraft, can dock with Hubble. And when they do that, the main point behind that is sometime late in the next decade, they're going to have to put an engine on Hubble to safely deorbit it when its lifespan is over. So that they can bring it down to Earth without it crashing into someone's home. Well, I personally think it's very likely that if we don't have another optical telescope planned by the end of the next decade, people are going to start talking about doing that maintenance mission, and maybe let's give some additional more servicing, maybe even with a robot at that time. This image is a theory, but I think that this telescope will not die so quickly. In fact, the telescope I've shown doesn't die at all very easily. So what does all this stuff have to do with this image of me, incredibly dirty, in a cave? I mean, and how does it have anything to do, well, it has a lot to do with this image. This is Lyman Spitzer. I'm almost done. This is Lyman Spitzer. He was also a rock climber. This is him in the gunks doing rock climbing in the 50s. He actually did some major climbs. He did a first ascent of Mount Thor on Baffin Island, several expeditions. He's a major climber. This is Bob Odell. Bob Odell he didn't like rock climbing. He went once with Spitzer. But he was also he literally wrote the book on competitive aerobatic flying, trying to do things with a plane that no one had ever done before. This is a plane he owned. He bought it as a kid. He then did so much redesign and rebuilding of it that the FAA considers him the builder. Both of these men, by the way, were like Moses. When Hubble was finally launched, neither of them got to benefit from it. They were already out of the program for many complicated, tragic reasons. The telescope almost destroyed Odell's career. Spitzer was too old by the time it was launched and did very little research with it. But all three of these images, me, Spitzer, and Odell, have a great thing in common. They all have to do about the same thing. And they have the same thing to do with this image as well. Because all three of those images have to do with trying to do something that's never been done before. And this is an image of what we could see before Hubble, and it was an effort to see something that no one had ever seen before. Let me go close. This is the Pillsbury Doughboy as the best image that Gavriola in 1945 could get us. When Hubble was fixed in 1993, one of the very first images it took was of this star. The name of the star is, you might know it, is called Eta Carina. This was the image of that star. Let's go back. See the two stars on the top? See the two stars there? That's a picture of a star exploding. That is reality. That is truth. You're now getting to see what the universe actually looks like. That's what this is all about. To go where no one's ever gone, to push the unknown, to see things none of us have ever seen. That's why this is done. That's why I like to cave. I'm going places no one's ever seen. I've actually been able to cave more than 30. I've been on a project that's discovered more than 35 miles of virgin passage in caves in West Virginia in the last 6 years. That's why Spitzer built the telescope. That's why he went mountain climbing. Same with Odell. Odell was willing to sacrifice his career to get this telescope built so we could see images like that of a star exploding. You could see, by the way, the images coming out of these two expanding cones coming out of the center and jets flying. It's incredible. It's also why we go here. One of the components of this I want to mention is that it is fun. We all love looking at these images. These astronauts are doing real scientific research, as the astronomers are, but they're having a ball. And we as Americans and as citizens of Earth are having a ball experiencing it with them. It's why someday we want to go here to Mars. You know, this is a picture that was taken by the European Mars Express, and you can see what looked like ice floes frozen in the surface. This is not in the Arctic regions of Mars, by the way. We have a Phoenix lander right now that is in the Arctic regions. We're getting the first touch of ice. The first time a human spacecraft has actually touched ice on another planet. Because we want to go. I like to say we want to trace a warm line of life where there is none. This is Europa. We want to go there. This is not a Hubble picture book. Right? This is from Galileo. Because this planet might have an undersurface ocean. Red material leaks up through these cracks. We have no idea what that red material is. Don't you want to go and find out? Crab Nebula. This is a Hubble image. We want to get an idea of what's going on there. There's the neutron star in the center. This does strange things. It would be nice to get close to it. And maybe go to galaxies. We should not put limits on where we can go. Robert Heinlein wrote a book called The Rolling Stones. It was one of his teenage science fiction books from the 50s. It was about these two teenagers, twins, who live in a spaceship. Their father basically runs a cargo ferrying system business from Venus to the Earth. And one day they got to go out and do work on the outside. They got to do a spacewalk, and they're just doing work. This is just a chore they have to do. And they suddenly stop and look at the sky around them in space. And their response was this. This is Heinlein. It was an enormous room, furnished in splendor, though not fully inhabited. It was their own room to live in, to do as they liked. And that's what the universe is all about, and that's what all this exploration is about, is to go, to visit that mighty room and see what no one has ever seen before. Thank you very much. Did I go long? All right. Thank you.
Thank you, Bob.
Thank you.
What an inspiration.
Thank you.
I'd like to present on behalf of the Explorers Club a certificate of appreciation for you.
Thank you, sir.
Look forward to hearing you again soon.
Oh, thank you very much. I'd love to. Thank you. Thank you very much. Oh, absolutely. I'll answer questions as long as people want.
We have time for a few questions. And then after this, I believe the book is available.
Yes, the book is available. In fact, people can buy my books if they wish. That's absolutely the case. So, shall I ask, or will you call people?
You want to go ahead?
What are the first people that were in space doing at the moment? What are the last people that are going into space?
Right this moment?
Yeah. What are the Russians doing?
Oh, I see what you mean. Well, okay, I'll repeat the question. I'll repeat it. He wants to know what's going on right now with other nations in space. Is that how you...
The Russians?
The Russians, the Chinese.
And the latter people, the Chinese and the Indians.
Okay. It's an interesting situation. I've written an essay on this called The New Colonial Movement. What we actually have is something very comparable to what's happening in the 1800s. There is a vacuum in space, and many nations in the world want to occupy that vacuum. The difference is there are no aboriginal people. It's just empty land, and everyone wants an opportunity to grab it. And so the Chinese have an aggressive space program. They have sent men into space. They're going to have, this October, they're going to do their third mission in which they're going to do spacewalks for the first time. The Indians have they are the dark horse in this whole thing. No one pays much attention to the Indians, but they actually have a very vigorous program that is centered on making profit, which is very interesting. It's a government program, but it's commercial in nature, and they want to have a very successful program. They actually have no plans at the moment to send men in space, but they talk about it. If you read Indian newspapers on the web, they're space crazy. They want to go. So they're an interesting, those two nations. But you can't exclude Japan, which is very embarrassed by the fact that China has superseded them. You can't leave the Europeans out. The British, who for decades were by law forbidden to send government astronauts into space, have started suddenly to look at that and rethink it. And what's going on is that people are beginning to recognize that this is going to happen. And if we don't get in on the game, we're going to miss out, and everyone wants to be in on it. And I'll repeat, it's not just political strategy, and it's not just power. It is also everyone wants to have the fun of doing it. That's always a component. We can't forget that. Other questions? I'm sorry. Shall I? In the back.
What was the Hubble named after, and why was it not named after Lyman Spitzer?
Oh, that's a good question. The question is, why was Hubble named as it is, and why was it named after Lyman Spitzer? Well, First of all, it would have been a little embarrassing to name it after Lyman Spitzer. They made the decision to name it Hubble after Edwin Hubble, who was probably the greatest astronomer in the last 200 years, one of the greatest astronomers, an American astronomer. They wanted to honor Hubble in that way. There is a funny story having to do with the building of the Hubble Space Telescope, though. In its early years, they called it the Large Space Telescope, before they had named it, whose initials are LST. And many people in the program used to joke that really stood for Lyman Spitzer Telescope. And no one objected because they thought he deserved it. In the end, they named the telescope that's in orbit. It's an infrared telescope. Now it's in orbit called the Lyman Spitzer Telescope. That was in honor of Lyman Spitzer for this purpose. Yes, over here.
So what is the diameter of the main lens, big lens?
You know, I'm glad you asked that question. I completely forgot to tell you. The actual lens, the mirror, the primary mirror, is 93 inches across, which originally was going to be 120 meters across, which is 3 meters across, about 120 inches, which would have put it at the time when it was launched among the top 5 telescopes in the world. But because of all those budget battles in the 70s, the astronomers made a decision to shrink the size to 2.4 meters, which is 93 inches, to reduce the costs. It actually solved a great many engineering problems in terms of using it with the shuttle, and so that was a compromise they made to get funding. And actually, in many ways, it was a smart engineering decision because a 120-inch telescope would have been extremely difficult to put inside the shuttle and get up into space. So they actually solved problems by doing it that way. Other questions? Yes?
When will we start seeing pictures from the segmented Earth-based telescopes?
Okay, well, there are ground-based telescopes today. The question is, when will we start seeing segmented images from segmented ground-based telescopes? They've been doing it for probably 2 decades. The Keck telescope is a segmented telescope. Ground-based telescopes today are getting very big and very sophisticated and can do remarkable things. But they cannot give you the resolution of a telescope out of the atmosphere because of the atmosphere, even when they are 4 to 5 times bigger than Hubble in size. They just can't do it because the atmosphere shakes the image too much. Now, they have something called adaptive optics, they call, which is using computers to try to fix the problem, but that only works in the infrared. Because in doing it in optical wavelengths, it requires too much computer power, and it requires very small fields of view, which means you can't do big surveys. You can't look at things like the Orion Nebula and see them sharply. It has only limited uses. So it does not, and probably will not for decades, replace telescopes above the atmosphere. Other questions? Over here.
Yeah, just 2 more questions after this, because we want to get you outside.
Okay.
I must admit that after reading the review of the book in New Scientist, I bought the book, so I'm not going to buy it tonight.
Okay.
But I know you have other books, because Rob mentioned in his introduction. If we want to buy those books, where does one go to get those books? Because I've tried getting them, and I can't seem to buy one. Do you have a website or something? I have a website.
You can go to my website to buy my other books. I do have a very limited number of copies of my other books here, and you can buy them from me if you wish. But if you want, just get the way to get to my website, the easiest way I tell people to do it is you do a Google search for Zimmerman Bibliography, and you find the Zimmerman Bibliography. That's my webpage, and you can buy the books through there. And you can get my email address off of that. And there's also a postcard out there for buy this book if they run out of copies. If you contact me through my website, I can absolutely arrange to sell you books if you want. Thank you very much. Other questions? Any other questions out there? Yes, in the back.
That'll be the last question, and then we'll adjourn for cocktails and reception.
What do you think of this thing, the collider that's been built under the Swiss-French border, and they're going to turn it on in August, and some people are afraid it's going to create a huge black hole. It's going to suck in.
The question is, are we all going to die? I understand. There's a super collider, a very large new super collider that's being built in Swiss Alps. The Europeans have moved forward on physics research, and they're going to turn it on in August. And there are some very fear-mongering, I like to call it. There is probably very, 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 very. It's not going to happen. I don't know a lot about physics, but I'm willing to bet my bottom dollar that's not going to happen. What it is going to do is it's actually where the United States has not moved forward. hey, building one of those super colliders is extremely expensive, and you have to have a big government project. And we made a choice, and some people have valid, correct choice, or maybe people can disagree, but we made a choice that we didn't want to spend the money for such a thing, that we're going to build one in Texas, and they decided not to in the late 80s. In the mid-90s. But the Europeans have moved forward, and it's possibly going to find new physics, answer some other questions. What it'll most likely do is answer a few questions and raise a lot more. That's the way science works. That's the way everything works. Thank you all for having me. I hope you enjoyed our talk.